Application of artificial intelligence to the electrocardiogram. Artificial intelligence, AI, has given the electrocardiogram, ECG, and clinicians reading them superhuman diagnostic abilities. Trained without hard-coded rules by finding often subclinical patterns in huge datasets, AI transforms the ECG, a ubiquitous, non-invasive cardiac test that is integrated into practice workflows, into a screening tool and predictor of cardiac and non-cardiac diseases, often in asymptomatic individuals. This review describes the mathematical background behind supervised AI algorithms, and discusses selected AI ECG cardiac screening algorithms including those for the detection of left ventricular dysfunction, episodic atrial fibrillation from a tracing recorded during normal sinus rhythm, and other structural and valvular diseases. The ability to learn from big data sets, without the need to understand the biological mechanism, has created opportunities for detecting non-cardiac diseases as COVID-19 and introduced challenges with regards to data privacy. Like all medical tests, the AI ECG must be carefully vetted and validated in real-world clinical environments. Finally, with mobile form factors that allow acquisition of medical-grade ECGs from smartphones and wearables, the use of AI may enable massive scalability to democratize healthcare. The application of artificial intelligence to the standard electrocardiogram enables it to diagnose conditions not previously identifiable by an electrocardiogram, or to do so with a greater performance than previously possible. This includes identification of the current rhythm, identification of episodic atrial fibrillation from an ECG acquired during sinus rhythm, the presence of ventricular dysfunction, low ejection fraction, the presence of valvular heart disease, channelopathies, even when electrocardiographically concealed, and the presence of hypertrophic cardiomyopathy. Despite the fact that the electrocardiogram, ECG, has been in use for over 100 years and is a central tool in clinical medicine, we are only now beginning to unleash its full potential with the application of artificial intelligence, AI. The ECG is the cumulative recording at a distance, the body surface, of the action potentials of millions of individual cardiomyocytes, Figure 1. Traditionally, clinicians have been trained to identify specific features such as ST segment elevation for acute myocardial infarction, T-wave changes to suggest potassium abnormalities, and other gross deviations to identify specific clinical entities. By their very nature, the magnitude of the changes must be substantial in order to significantly alter a named ECG feature to result in a clinical diagnosis. With the application of convolutional neural networks to an otherwise standard ECG, multiple nonlinear potentially interrelated variations can be recognized in an ECG. Thus, neural networks have been used to identify a person's sex with startling precision, area under the curve, AUC, 0.97, recognize the presence of left ventricular dysfunction, uncover the presence of silent arrhythmia not present at the time of the recording, as well as identify the presence of non-cardiac conditions such as cirrhosis. Many biological phenomena, each of which can leave its imprint on cardiomyocytes' electrical function in a unique manner, lead to multiple, subtle, nonlinear, subclinical ECG changes. Although ECGs are filtered between 0.05 and 100 Hz to augment capture of cardiac signals, they likely also are influenced directly and indirectly by nerve activity, myopotentials, as well as anatomic considerations such as cardiac rotation, size, and surrounding body habitus. With large datasets to train a network as to the multiple and varied influences of each of these conditions, powerful diagnostic tools can be developed. In this review, we will offer an overview of machine learning, ML, show specific examples of conditions not previously diagnosed with an ECG that are now recognized, and provide an update of the application and practice and future directions of the AI-processed ECG, AI ECG. Broadly speaking, AI can be applied in two ways to the ECG. 4 and 1. currently performed human skills, such as determining arrhythmias or acute infarction, are performed in an automated manner, making those skills massively scalable. The second utilization is to extract information from an ECG beyond which a human can typically perform. In this review, we will focus on the latter. Figure 1 microelectrodes in a single myocyte, top left, record and action potential, depicted middle panel. Ionic currents and their propagation are sensitive to cardiac and non-cardiac conditions and structural changes. When the aggregated action potentials are recorded at the body surface. Top right, the ensuring tracing is the electrocardiogram, bottom. ECG, electrocardiogram. Machine learning introduction. The term machine learning was coined more than 70 years ago to describe the ability of man-made machines to learn how to perform complex tasks, and to improve task performance based on additional experience. Practically, it refers to replacing algorithms that define the relationship between inputs and outputs using man-made rules with statistical tools that identify, learn, the most probable relationship between input and output based on repeated exposure to exemplar data elements. As with other revolutionary ideas, when first introduced, it was ahead of its time, and the data and computing power required to enable this revolution did not exist. Today, with exponentially growing digital datasets and a significant increase in the computational power available to train networks, ML, sometimes referred to as AI, performs highly complex tasks. In supervised ML, the task is defined as an optimization problem, which seeks to find the optimal solution using labeled data. By defining a loss function or a matrix of how well the machine performs a task and minimizing the error and maximizing the success matrix, a complex task is transformed into a mathematical problem. Most ML models are parametric and define a function between an input space and an output space. In neural networks, designed to mimic human visual cortex, each neuron is a simple mathematical equation with parameters that are adjusting during network training. When the neurons are connected in many layers, it is referred to as a deep network. The function applies parameters to the input in linear and nonlinear ways to derive an estimated output. Figure 2. Figure 2. A convolutional neural network is trained by feeding in labeled data, in this case voltage time waveforms, and through repetition it identifies the patterns in the data that are associated with the data labels, in this example, heart pump strength, or ejection fraction. The network has two components, convolution layers that extract image components to create the artificial intelligence features, and the fully connected layers that comprise the model that leads to the network output. While large data sets and robust computing are required to train networks, once trained, the computation requirements are substantially reduced, permitting smartphone application. AI, artificial intelligence, EF, ejection fraction. During the learning phase, both the inputs and the outputs are shown to the function, and the parameters, sometimes called weights, are adjusted in an iterative manner, to minimize the difference between the estimated output and the known outputs. This learning or training phase often requires large data sets and robust computing power. The most common way to adjust these weights is by applying a gradient-based optimization method, which adjusts each parameter weight based on its effect on the error, with the network weights iteratively adjusted until an error minimum is found. Once the learning phase is complete, the parameters are set, and the function becomes a simple deterministic algorithm that can be applied to any unseen input. The computing power required to deploy a trained network is modest and can often be performed from a smartphone. A neural network is composed of different nodes, representing neurons, connected to each other in a directed way, where each node calculates a function of its input based on an embedded changeable parameter, weight, followed by a nonlinear function, and the inputs flow from one set of neurons, called a layer, to the next. Each layer calculates an intermediate function of the inputs, features, and the final layer is responsible to calculate the final output. In some architectures, the neurons are connected to each other to enable determination of temporal patterns, recurrent neural networks, used when the input is a time series. Others, such as convolutional neural networks, originally developed for computer vision tasks, have also been used for natural language processing, video analysis, and time series. As these models are mathematical functions, the inputs are comprised of real numbers created by sampling physical signals. For example, an ECG is converted to a time series sampled at a consistent sampling frequency in which each sample represents the signal amplitude for a given time point. For a 10s12 lead ECG sampled at 500 Hz, the digital representation of the input is a matrix with 5,000 samples, 500 Hz times 10s, per lead. With 12 leads, the final input will be a set of 60,000 numbers, 5,000 by 12. For binary models in which the output is yes/no, such as the presence of silent atrial fibrillation, AF, determined from an ECG acquired in sinus rhythm, the input numbers, i.e. the digital ECG, are used by the network to calculate the probability of silent AF. The output will be a single number, ranging from 0, no silent AF, to 1, silent AF present. To dichotomize the output, a threshold value determines whether the model output is positive or negative. By adjusting the threshold, the test can be made more sensitive, with more samples considered positive and fewer missed events, but at the cost of a higher number of false positives, or alternatively, more specific, with fewer false positives but more missed events. Since the training of supervised ML models requires only labeled data, e.g. ECGs and associated ejection fraction, EF, values, and no explicit rules, machines learn to solve tasks that humans don't know how to solve, giving the machines, and humans who use them, what appear to be superhuman abilities.